We'll continue right away. We're on talking about the dot product, and today we're going to be doing a few applications of the dot product, specifically about calculating the projection of one vector onto another. So what do we mean by this, the projection? And I'll tell you about that first. So let's go back to the book, and here's the important diagram to keep in mind. So here's the situation. We have two vectors. Imagine for a moment that we have this blue vector that I'm going to draw in a moment. That's the vector v, that you see it on the screen already, this vector v. And you have another vector, this vector u. And what we mean by projection is, the best way to explain it probably is like the picture you see on the screen right now. Imagine that there's a flashlight, and that flashlight is illuminating in a direction perpendicular to V, right? So if V is horizontal in this case, you want the flashlight to be vertical, right? And imagine that that flashlight is very, very far away on the top. I mean, obviously it doesn't show like that in our picture, but because we have limited space in the book, but imagine that the flashlight is super, super far away up. And then you see the shade. You want to look at the shade of this red vector. So what is the shade of that red vector? I'm going to draw it with brown. So if you project the shade is going to look like this, right? And so that's exactly what we want to figure out. How can we figure out the projection? That's the correct name. The projection of the vector u onto the vector v. So that's the question we want to answer. How can we find, I'll write it on the page so we're ready. How can we find the projection of vector u onto vector v? All right, that's the question we want to answer. And let's try to figure it out. And we're gonna do it by cases. So let me erase my drawings here and then show you these pictures on the right. It illustrates two possible situations, right? The picture on the left illustrates the situation when the angle from u to v is acute between 0 and pi over 2. And that's like the first one we did, right? You get this gray vector would be the projection. And the picture on the right is when the angle is greater than pi over 2. By the way, if the angle is exactly pi over 2, so if the vector u is perpendicular to the vector v, then the shade will be nothing, right? It's kind of like what happens when the sun is at noon, right there at the apex, right? You don't have a shadow, right? When the sun is exactly on top of the vector, you get 0 shadow, right? So if for 90 degrees for pi over 2, you get no shadow, and that's very easy. In that case, the projection is just 0, the 0 vector. And so the picture on the right shows you what happens when the projection is, when the angle is more than 90 degrees, when the angle is obtuse. And in that case, the shadow points in the opposite direction of B, as you can tell, right? So in this, when the angle is acute, it goes in the same direction. When the angle is obtuse, it goes in the opposite direction, okay? So let's try to figure it out on our own. What would the formulas be? So we have the vector v, and I'm gonna draw it a little bit crooked so you don't imagine that it's always horizontal or vertical, okay? So here's a vector v, and here's a vector u. And I'm gonna do the case where the angle theta is between 0 and 90 degrees. So the picture looks like this. And remember, the flashlight comes from a perpendicular direction. So the light of the flashlight comes from this direction. Right? Perpendicular. And when we do that, the shadow will look like this, right? So there's 90 degrees here, and this is the vector we want to find out. And first of all, we have a name for that vector. We call it, here's the way we're gonna denote it. That projection vector is gonna have this name. It's gonna be called the projection, P-R-O-J, of vector U onto vector V. Kind of clear, right? If you get used to it, it's not going to take a lot to get used to it. So it's a projection of this vector U onto the little vector V, right? So this one onto that one, the big one onto the little one. And we want to find out what it is. So what is that? How can we find it? All right. And at least in this case, see, it's not going to be that difficult. How are we going to do it? Well, we're going to ask ourselves two questions. Question now, what is its magnitude? And question two, what is its direction, right? Remember, vectors have only two properties, magnitude and direction. So if we get to answer both of them, we're set. So we want to find out the answers to those two questions. So what is its magnitude? What is its magnitude? And what is its direction? Now, the direction question, that's the easiest, right? What is it? What is the direction of this projection vector? The direction of say it again. So I didn't hear that. So the direction of this purple one, we can tell, obviously, by construction, is the same as the direction of V, right? So the direction is super easy. Exactly. Thank you, Michael. Yes. So what is the direction? That's super easy. The same as V. The same as V. So that's easy. So all we need to know now is, so then now we have a plan. What is going to be our plan to figure it out? Well, we already know it's in the direction of V. So first we make the direction of V into a unit vector. How do we do that? We just take V and divide by its magnitude, right? Or multiply by 1 over its magnitude. If we do that, then we have a unit vector in the direction of V. And then we simply multiply by its magnitude, and voila, we got the projection, right? So all we need to do then is find out the magnitude. And the magnitude, the answer to the magnitude question, we call it, so the magnitude, the answer to the magnitude question, we call it the scalar. So this one over here is called the scalar of U with respect to V. So we're gonna call it the scalar of U and V. So that's, by definition, this is the magnitude of the projection vector. All right. And let's figure that one out. That one is also not that difficult, right? How do we do it? Well, we are going to use the cosine of the angle, right? So we have a right triangle right here. And from this right triangle, what is the cosine of theta? Well, cosine of theta is adjacent under hypotenuse, right? So this is the length of the projection. So the length of the projection vector divided by the length of the u, that's the hypotenuse. Yes? So then this is the scalar. And this is the magnitude of u. So then I can solve for the scalar, right? I can solve for this. And it will be magnitude of u times cosine theta. All right. Very good. So I think we're ready to put it together. So how do we put it together? Well, we're going to follow up on our plan, right? So how do we get the projection vector? We take v and we divide by its magnitude to make it unit. And then we multiply by the magnitude we want. And the magnitude we want is this one. So let's write down the plan. So plan to find the projection vector. Take v, multiply by 1 over v to make it unit. And then multiply by scalar, which is u cosine theta, so that it has the right magnitude. Okay, perfect. So let's do it. So let's see. We're finally able to write it down. So the projection will be take v and divide by its magnitude, and then multiply by the scalar. But the scalar is u times cosine, so this is going to be this. Let's put it all. U cosine theta divided by v times v. Write it like this. Okay. So that's exactly, so that's it. We figured it out. That is the projection vector. That's a way to get the projection vector. So we have this number. This is a constant. This is its magnitude. And we're multiplying by the vector v. So it points in the same direction as v. All right? Now, we have to be careful because we only did this in this case where the projection was with a smaller angle, right? We still need to do the other case when the angle is bigger than 180 degrees. But I'm going to spare you the details. So it turns out that the answer is essentially the same. So the only difference is going to be that the scalar, so the scalar is going to be negative over here. So when the scalar will be negative because we're going to be on the opposite direction, right? So the scalar, instead of being this, the scalar will be negative, all right? So I'm not going to do the details. I'm just going to write it here. If the angle is bigger than 90 degrees, theta is bigger than 90 degrees and smaller than pi, then scalar is simply minus u cosine theta. No, sorry, it's the same. So even though it's negative because it's going to point in the opposite direction, the cosine of the angle will be negative number. So it's still the same. So it's actually, so we don't have a negative sign. I was saying it incorrectly. Okay, so maybe we should see it. In fact, let's actually check it. Let's do it. I think we have, usually we don't have the time, but maybe I think we can do it. So let's do the other case. What would be the other case? So we're gonna need a new picture, and I'm still gonna make it. So we have our vector v, and let's imagine that now our u is like this. Right? The angle is more than 90 degrees. This angle theta satisfies that it is bigger than 90 degrees. Write it here, so we don't need that. So pi over 2 less than pi. So how do we find out the projection? So we still project at perpendicular to the vector v. So this guy over here falls perpendicular, and this is our answer. This is the vector we want. Okay, and we're gonna answer the same questions as with the previous case. So what is its direction and what is its magnitude? Now the direction now it's opposite of v, right? So direction is the same as negative v. It's the opposite of v. And magnitude, well, for the magnitude we can do the same way we did it, right? We can do we can look at the cosine of this angle. So if this is theta, this angle over here is pi minus theta, right? And if we do cosine of pi minus theta, that would be the adjacent, which is the magnitude. So that's the scalar, not the scalar, the magnitude of the projection vector. Divided by the magnitude of u. All right? And the only thing is that the cosine of pi minus theta is minus the cosine of theta. So this is minus the cosine of theta, right? So then if you solve for the projection, for the magnitude, would be minus magnitude of u cosine of theta. So now we're in the position of getting the projection vector. So we'll do the same technique. The projection vector, what we do is we take v, we divide by its magnitude to make it unit, but we put a minus sign before it because we want it to point in the opposite direction. And then we multiply by its magnitude. And we have it right here. So the answer is minus times minus cancel. So we get u cosine theta divided by magnitude of v, all of that times v. All right. So the same formula. Okay. So it didn't matter that we did it pointing one way or pointing the other way around. In both cases, let me show you the other one. I have it right here. So here's the one we did before. Right here. So if you compare these two, they're the same. They're exactly the same formula, right? So it's the magnitude of u times cosine over the magnitude of v times v. That's the same one for both. The book actually writes it like, let me write it the way it's written in the book. The book, I don't know exactly why. I kind of like to write the number and then the vector. But the book writes it like this. It writes it like as u cosine theta times v over magnitude of v. and which is the same over here. U cosine theta times V over the magnitude of V. All right. Okay, so that's it. And for both of these examples, the scalar is simply what you multiply the vector V. So the scalar is U cosine theta. So that's how big the the projection vector is, accounting for its sign. So where is exactly the definition? Let me take a look at it. So the scalar component is equal to where is exactly? Well, I'm going to show it to you in the screen in just a moment, but I want to make some simplifications first. All right, so let's summarize the work we just did right now. It didn't matter what angle we picked. In fact, it also now works for angle pi over 2. If you pick pi over 2, this is going to be 0. So, and then the projection is 0, just like we said. So here we go. Let's summarize it here. So in general, for any theta, the projection of U onto V is this number, right? Magnitude of U times cosine theta times the vector V over magnitude of V. Right, that happens in general. And in general as well, the scalar, so the scalar is, in general is what you multiply by that unit vector, right? So this is in general the scalar. So this is the unit vector, and this is what you're multiplying that unit vector to get it. But it accounts for its sign, right? So if the scalar is positive, that means you're going the direction of V. But if the scalar is negative, you go in the opposite direction of V. All right? So that is it. This is the formula. And then what we want to do now is simplify it a little bit more using what we learned last class. What did we learn last class? Well, last class we learned how to calculate the angle between two vectors using the dot product, right? So from last class, we learned that if we do U dot V, we get magnitude of U times magnitude of V times cosine theta, right? And you see, this is almost like that one. So the idea is if we can solve for this and eliminate the angle, because the angle is different, it's difficult, right? We in general don't have a tool, you know, a good tool to figure out the angle. But what we can do here is solve for U cosine theta. If we solve for U cosine theta, this will give me U dot V divided by magnitude of V, right? And then put that in here. So this is an alternative formula for the scalar, by the way, right? Because U times cosine is equal to the scalar. So that's a new formula for the scalar. A new formula for the scalar you can use that does not involve theta. It's without having theta, right? And then if we put that in here, what do we get? Well, we get U dot V divided by magnitude of V times V over magnitude of V, right? Now, remember, this is a number, that's a number, that's a number, that's a vector, right? So we can combine these two together, and it looks like this. It looks like U dot V times magnitude of V squared times V. And then in an even better way, what is V? What is the magnitude of V squared? Let's try to remember that. So what is the magnitude of V? Well, the magnitude of V is a square root, right? The first coordinate square, the first component, the second component square, and the third component square, right? And so if we square it, that's just v1 squared plus v2 squared plus v3 squared, which, if you think about it, is the same as v1 times v1 plus v2 times v2 plus v3 times v3. So it kind of is a dot product, right? Which dot product? Well, the dot product of v with itself. So this is v dot v. And that's the last thing we can do to make it look like an even better formula, right? So we can, instead of writing the magnitude of v squared here, we can write v dot v. And this gives us the ultimate formula for the projection, the one that looks the prettiest, in my opinion. I'm gonna write it right here. The projection of vector u onto vector v is equal to u dot v divided by v dot v times the vector v, right? That's the formula that I like the best. Okay, all right. Let me show you a screen that summarizes all that we've seen right here, and then we'll see some examples. Okay, so let's go back to the book right here. Okay, so let's go over it. So first, this is the first formula we found out. What is a projection? The projection is magnitude of u times cosine times v over magnitude of v. And what we said is that we can also calculate it this way. It's the scalar times v over v, because that's the unit vector in the correct direction. And we can calculate it, the scalar can be calculated in this cute way, which is simply not the scalar, all of this constant that multiplies this vector v in this way, which is just u dot v divided by v dot v. And then the scalar component of u in the direction of v. So in other words, how big and in which direction is the projection. And that's simply this number, magnitude of u times cosine, and that can be written with the way we define the dot product as u dot v divided by magnitude of v. All right? So this box is what you need to know. I want to give you the impression that this is not complicated. I mean, it looks complicated because we have all of these new definitions that you're not familiar with, you know, the projection and the scalar, but in reality it's simple. It's just a simple way of looking how you can find out the length of one of the sides of a right triangle, right? If you know the angle in between. That's essentially all the important things that we did. So let's do an example. This one that follows right here. It says, find the projection of u onto v and the scalar of u onto v for the following vectors. Illustrate each result. So the vector u is 4,1, the vector v is 3,4, the vector u is -4, -3, the vector v is 1, -1. All right? So let's do it. So starting with part A, the vector u is 4,1, vector v is 3,4. All right, let's switch to the page. Okay, good. So first we want to figure out, so we have tons of ways of doing this. So let's figure out the projection directly. So what is the projection of u onto v? And the last formula we learned, which is the one that I like the best, says that is the following, is u dot v divided by v dot v vector v. That's my favorite because it's the easiest to use. So what is u dot v? Right here is 4,1 dot 34. And in the bottom, we have v dot v. That's 34 dot 34. And once you've done that, you multiply that number by v, which is 3, 4. All right, so let's do the dot product. This is 4 times 3 plus 1 times 4. And in the bottom, 3 times 3 plus 4 times 4. And whatever that number is, we multiply it by 3, 4. And what is that number? Well, that number is 4 times 3, 12, plus 4, 16. 3 times 3, 9, plus 4 times 4, 16. 16 plus 9, that's 25. So it's 16/25 of 3, 4. So that would be 48 over 25 and 64 over 25. That is the answer, right? Now, what about the scalar? Well, the scalar is what you're supposed to multiply the original vector, right? So scalar, we can recalculate with the formulas that we know, or we can just figure it out from our previous answer, right? So based, if we wanted to figure it out on our previous answer, it's super easy, because what is the number you multiply b? So this is v, right? What number do you multiply v to get the projection? And the number is 16 over 25. So that's the easiest way, the way in which you already use what you did before. But if you want to recalculate it, you can use it with this formula. This is u dot v divided by magnitude of v. And u dot v is 4 times 3 plus 1 times 4 divided by magnitude of v, which is 3 squared plus 4 squared. So this is 12 plus 4, 16. And this is magnitude of v. This is 25, so it's 16/5. Oh, my bad. So there's something I didn't do here. So it's not 16/25. Hold on a sec. It's 16 over 5. And then let me reconcile with that other part. Why? What is it? Oh, yes, my bad. So you're not supposed to, it's not the number that multiplies times v, it's the number that multiplies times a unit vector, right? So I said something wrong. So it's not the number that multiplies v, it's the number that multiplies a unit vector pointing in the direction of v, right? So to make this into a unit vector, you would need to divide by its magnitude, which is 5, right? So so that's why it has to be this number over here. So in other words, how do I do it? Yeah, so here's how you reconcile it. So this vector 3, 4 has length 5. So it's really 5 times 3/5, 4/5. This is a unit. This is a unit vector. So then if I go back here to the projection one, so the projection one is 16/25 times 5 3/5, 4/5. That's a unit one. And this is 16/5. And now it's what I was telling you, right? So this is a unit vector pointing in the direction of v. And what is the constant? What is the scalar that you multiply by? 16/5. That's this one over here. All right? Questions? Let's do part B. So for part B, u equals -4, -3. And v equals 1, -1. And it's the same question. We want to find out both the scalar and the projection. So let's start with the projection. What is the projection? Well, we said is u dot v divided by v dot v times the vector v. So this would be -4 times 1 plus -3 times -1 divided by v times v. That's 1 times 1 plus -1 times -1. All of that times the vector 1, -1. It's -4 plus 3 divided by 2. So this is -1/2 that multiplies the vector 1, -1. That's -1/2, 1/2. And that's it. Now, if you want the projection, you can make this unit vector and see what's the constant you multiply by. That's one way. Or the other way is to recalculate it directly, right? If you want to recalculate directly, that's simply is u dot v divided by magnitude of v. And u dot v, we did it, it was -1. And magnitude of v is the square root of 1 plus 1. This is -1 over root 2. If the scalar is negative, that means your projection is of something with angle bigger than 90 degrees. If the scalar is positive, like this one here, it means the angle was smaller than 90 degrees. So let me show you the pictures that correspond to this, and then we'll take some questions. So let's go to the book. So this is the first one we did. We have the vector 4, 1 being projected into the vector 3, 4. So the light is coming from this direction. Let me annotate it here. Maybe a big yellow, yeah, so perpendicular to this. So it sort of comes from this direction, the light, right? And my yellow arrow that's the light. And then the light comes from that direction. It creates this shadow, the black vector. And that's the one we calculated. That vector was 16/25 of 3/4. So it's like take the vector 3, 4 and shrink it by a factor of 16/25. That's what we did. Okay, and then for the other one is in next page, the second one we did. So let's go to the next page. Good, so here it is. So this time we were projecting this red vector onto the blue one. And the light, in this case, would come from this direction. Right? So the light is coming from this direction. And that's why the shadow is not that big, right? It's a tiny shadow. This black vector is the shadow. And as you can tell, it points in the opposite direction of V. It points in the opposite direction because the angle between the two vectors is bigger than 90 degrees. So it points in the opposite direction. And the scalar that we're multiplying is -1 over root 2. So it's this vector is, how big that vector is 1 over root 2 times a unit vector, and the fact that it's negative means it points in the opposite direction of the vector b. Is that clear? Like it has, let me move, okay, there's a projection 1 as well, right? The projection 1 is -1/2 is the one we obtained. And like I said, so that's like taking a unit vector in the direction of v and multiplying it by -1 over √2. That's what the scalar factor means. All right, we have a bit of time still. So are there any questions so far? Okay. There is so I want, if there are no questions, I want to at least give a little brief introduction. Maybe we'll finish today's session a little bit ahead of time anyways, but I wanted to talk, I want to talk a little bit about the next section, because that one is a bit more involved, a bit more complicated in a certain sense. And we're going to learn about something called the cross product. And the cross product is only for vectors in three-dimensional space. So this one will only be for vectors in three-dimensional space. And the way it's going to work is as follows. So you're going to have vectors in three space. So vectors in three space means that they live, somewhere in three-dimensional space, and they're somewhere there, right? We can think that they have the same origin, like this. So they both have the same tail. And then the question is, what is the cross product? And the cross product of these two vectors will be another vector in three-dimensional space. And the important thing is, you know it, I need to tell you two things. I need to tell you its direction and its magnitude, right? Now, its magnitude is not going to be a problem. It's going to be a formula. We'll talk about it tomorrow. I mean, next week. It will be a formula that will depend on these two. But the direction is what is interesting here. So what is going to be the direction of this vector u cross v? So imagine that the purple one is u and the black one is v, right? And here's how you can get the direction. So you're going to use your right hand, we're going to use the right hand rule. And it works like this. You start at u, so I'm going to align my hand in u. I go from u to v, right? U to v. And as I'm going from u to v, I check where my thumb points. So as I'm going from u to v, where is my thumb pointing? And where my thumb is pointing, that's going to be the direction of the cross product. So the cross product will be perpendicular to these two. So it's perpendicular to u and v, and it points in the direction followed by the right hand rule. Okay, let me show some better pictures from the book. So here's the definition. So it's the cross product, like I was telling you, the cross product of u and v. And here it's its magnitude. I mean, I didn't tell you about the magnitude. The magnitude of u cross v is the magnitude of u times the magnitude of v times the sine of theta. It looks a lot like the dot product, if you were to ask me, right? It's very similar to the one for the dot product, except the one for the dot product had cosine here. It was cosine theta. This one is different. It has sine, right? Sine instead of cosine. Then that's the magnitude. See, but here's another important distinction between the dot product and the cross product. For the dot product, we have a vector and another vector. Dot product gives you a number, a scalar. Here, for the cross product, you have a vector, another vector, and the answer is a vector. All right? It's a more interesting product in that sense. You start from two vectors, and the answer is another vector. That's nice. So what other vector? Well, the other vector has this magnitude. And to figure out its direction, what we do is we follow the right-hand rule. And it's like I was telling you, right? You start from u. So in this picture, you would start by looking at u. So you would go from this vector u, and then you could go from u to rotate so that you go from u to v with your right hand, right? So as you rotate with your right hand from u to v, so you go from that yellow vector to this red one. As you rotate from u to v, where is your thumb pointing, right? And you can see it on the diagram right here on the book. So in this person, when it rotates its hand from u to v, the thumb points in the direction, in the perpendicular direction. That's going to be u cross v. So the answer to the problem will be a vector pointing in the blue direction, u cross v. Now, something very, very important here is that the order matters. For the first time, we have a product where the order is actually important, right? Because if you do it the other way around, if you go u, instead of you doing u cross v, you do v cross u, then your hand is gonna be pointing down, right? If you start from v and then you go towards u, now your thumb points downwards, right? So if you do v cross u, the other one, then the direction will be the opposite one. So in this product, u cross v is not the same as v cross u. It will not be commutative, okay? And that's actually important. Okay, so I'm going to stop it right here because I don't want to get into the heavy details of the cross product till we have a fresh class, because there's a lot to talk about. Okay, so are there any questions before we stop for today? Can we go back to the example, the very bottom portion? Absolutely. Let me put it on the screen. Right there.
Professor?
Yes.
Will we be given drawings to like figure out where the light is coming from, or will we have to figure those out ourselves?
You would need to figure those out yourselves. But
Okay.
it's not that hard. Just think of the perpendicular direction to the one that you're projecting onto, right? That's one way. The other is, notice how for me to do this example, I didn't need to do the drawing at all, right? You see, when we do this problem, I mean, I use the drawing to figure out the formula. But now that I know the formula, I can simply use the formula, which is kind of easy to remember because it has a certain symmetry to it, right? U dot v divided by v dot v. So to do this problem that you see on the screen right now, I didn't use the drawing. So you don't, so to answer your question, you don't actually need it, right? You can answer the questions without actually knowing the drawings. I mean, it helps to know what is it that you're calculating, right? It gives it a context, and that's important. Most of these, by the way, are tools that you're gonna need next semester, those of you that are taking Math 250. So you're gonna need to know this, and this will be a tool that you're gonna need to do other problems about understanding multivariable functions. So right now we're going over those tools that you're gonna need, but really they will come into fruition next semester. Right now it seems like we're learning this, but we're not really gonna use them that much, and you would be correct. Where this preparation for next semester, most of this material. Any more questions? All right, so you guys have a good weekend, and I'll see you next week.